thank you very much for the introduction, and thank you very much for the invitation. It's my first time in the conference also, so thank you. So today I'm going to speak about graph machine learning for short-term solar forecasting. Now, first thing I wanted to start is why is solar forecasting important? Well, first, solar production is highly variable due to weather conditions. For example, if a cloud is passing by, the production drops. But if we have rain or snow, the production drops. Just as an example, this year in Switzerland, on the 22nd of April, there was a shortfall of around 1.4 gigawatts in solar production. Now, Swiss Grid had to cover that shortfall in production. And that covered means that you need to fire up some contingency measure like power plants, and this costs several millions of francs. So now, why is solar forecasting important? Because it costs money. But more importantly than money is because if we're going to meet our sustainability measures by 2050, we need more and more renewable sources in the energy mix. And now, if we're going to have more solar, we need to accurately forecast this production in order to keep the balance between production and consumption in the grid. Just as a recap for solar forecasting, it can be divided by the forecasting horizon. First is up to 3 days ahead, where the state of the art is using numerical weather predictions coupled with machine learning models or statistical models. The main applications for this is day-ahead markets, unit commitment, and transmission scheduling. Now, for a shorter term horizon, is up to 6 hours ahead, mainly like intraday operations. State of the art are combining satellite images with cloud motion tracking and feeding that to numerical weather models. Main applications are for load forecasting and, of course, of trading of energy and power. Now, for very short-term forecast for horizons up to 30 minutes ahead, the state-of-the-art is using all the sky imagers coupled with numerical models. Main application for that is ramp events, like, for example, knowing when we have to fire up a plant or where we have to run down a generator, for example. Now, and the talk will focus on this horizon, on the short-term horizon or intraday horizon. Now, as I was saying, most of the classical approaches use a combination of numerical weather models with satellite images, and how it works is based on past satellite images. You can compute cloud motion vectors, and from these cloud motion vectors, you can feed them into the numerical weather model, and you propagate clouds into the future. Now, one of the main limitations of doing that is that the resolution, both in time and space, can be limited, because running these numerical weather models for a very high resolution can be very demanding. So at CSEM, we say, okay, what if we use another approach? What if we use another type of data sources? And one of these data sources can be a ground-based extension. So PV systems, the rooftop that you have at your homes, can be a very good sensor of irradiance. And the idea is to use these sensors to track clouds. Now, imagine that we have 2 sensors, and imagine that we have a cloud that is passing by, and we know the distance between these 2 sensors, and we know the speed of the cloud. So we could anticipate, okay, cloud is going to get in 1 hour or in 2 hours to point B. What if we have another sensor? Then we could use the information from the other 2 remaining sensors in order to track the clouds. So that's the basic idea. We use ground sensors to track the clouds. But now one question arises: what if we have more sensors? What if we have actually a dense network of sensors? How can we process all this information? And this is, as you guessed it, where neural networks come in, or graph neural networks come in. So what we want, or what the idea that we have, is to use a dense network of sensors of PV systems or weather stations. For PV systems, the measure is power production, but power is proportional to radiance. And in the weather stations, we can measure irradiance, temperature, wind speed, wind direction, pressure, and humidity. So all these variables, and we have a dense network of sensors. The idea is to track clouds based on this measurement. And that's where graph neural networks come in, where we can use to model the spatio-temporal relationships of this time series data. Now, I was saying that there is a limited resolution with satellite images. Even if the satellite images can be of high resolution, then running the numerical weather models can be of can run in high computational cost. Now, with this approach, we can improve both the temporal and the spatial resolution of forecast. One of the motivation is, for example, just in Switzerland, we have around 200 weather stations from Meteo Suisse. They are connected weather stations. But on the other hand, we have more than 200,000 PV systems connected to the grid. There are more, but just 200,000 connected, where we could have data all across Switzerland and providing measurements from the irradiance field. Now, with this approach, there's one challenge, and the challenge, of course, is in the data. So in order to train properly a good machine learning model, we would need clean data, nice time series where we could track the cloud movement or the drops in the power production or in the irradiance. However, most of the time we have something like this. We have incomplete data. We have gaps in the data. And why is that? Because sometimes there are problems in the communications. Sometimes for example, you go on vacation and you turn off your Wi-Fi. So you have, I don't know, 1, 2, 3 weeks without logging data. So basically in our problem, then the nodes set is changing over time. We have nodes that are appearing or disappearing in the measurement. And these gaps can be of only a few hours, but it can be also of a few weeks or a month in the year. So we need to deal also with that challenge. So now, the forecasting problem that we have is that from past measurements, let's say past time measurements, we want to forecast H time steps ahead. Now, the challenge is that in the past measurements, we have the node set, or the nodes are changing or could be changing over time. And we want to forecast on a fixed node set in the future. And we want to learn this function that maps from past measurement into the future measurements. Now, at CSEM, we've developed the Digerati solution. Digerati is a probabilistic short-time forecast solution. It forecasts irradiance on 6 hours ahead with a resolution of 15 minutes. This is the diagram of the main blocks of the solution. Now, the first block, the heterogeneous data embedding blocks, what it does, it takes the data from the different sources, from the nodes, or from the PV nodes, let's say, and from the weather station nodes. And since they are measuring different data, what it does is that it projects them or embeds this data into a common space. So now, once we have all these features or in this embedded common space, we need to also cope with the challenge of the changing node. And how do we do that? What we do is we do a clustering of the space where we create a fixed graph. And for each of the clusters in the space, the nodes, the clusters are, or the representative of the cluster are the red dots. And the blue dots are the nodes that are maybe changing at every time. So at every time, we take the local topology on the cell, and we compute aggregated features for all the nodes that are present at that time. Now, based on these features now on a fixed node set, we train a forecast model on the fixed graph, and we forecast signals, in this case irradiance, in the fixed graph. Now, the last block of the model, what it does, it's an interpolation model where we can have query points or coordinates in any location in Switzerland. And based on these locations and the forecasted signal on the fixed graph, we can forecast this. And finally, the output is the forecast of irradiance for 6 hours ahead in the point of interest. Now, I'm not going to go into the details of all the blocks, but I just wanted to explain a little bit about the forecasting model on the fixed graph. So for that, we use temporal spatial multi-window graph attention network. This network receives as input the past features for 6 hours, and also receives the clear sky irradiance. The clear sky irradiance is like the theoretical irradiance that we can achieve, but that can be computed. We only need to compute this at basically how based on the position of the sun, and it can be computed based on the coordinates of the point and on the hour of the day, and of course the time of the year. Now, is the first block again in the encoder is a temporal attention block, and the idea with this temporal attention block is to process the temporal relationships of all the time series that comes into the system. Now, the second block is the spatial attention block, where we have a special multi-window mechanism. Is instead of like a multi-head attention, or it's a multi-head attention, but it's only that each head is focused on one part of the forecasting horizon. For example, if in this case we have 6 hours ahead, we divide the forecast horizon into chunks of 2 hours, like the first 2 hours, then from 2 to 4 hours, and then 4 to 6 hours. And each attention head focuses on this forecasting horizon. And why is that? Because, for example, for very short-term horizons, for the 0 to 2 hours ahead, mostly you need data or features from your closest neighbors. You're just very close in the future, so with just nearest neighbors, it's okay. Now, for the further ahead horizons, you need nodes that might be further away, because you want to anticipate, okay, what's going to happen, so you want to see ahead. Okay, what if as cloud is in Basel, I want to see if it's reached to Lugano maybe in 2-3 hours later. So that's why the motivation that we have on doing this multiple attention heads. Now, the last part on the decoder are basically just MLP heads, and the idea is to combine these features that comes from the spatial attention block with the clear sky irradiance. And also, we produce quantile forecast. We don't only produce deterministic forecast, but we forecast the quantiles for the distribution of the signals. So that's also the multi-headed the quantiles. Now, this is an example of the current forecast that that's with Digerati. We output forecast of the median. So here in the example, we have in red the observed signal. In the solid blue is the forecasted median, and the confidence intervals are in the shadow region. For confidence intervals, we output the 95 percentile and the 5 percentile as the confidence intervals. And this is an example for the same day. First, the forecast at 6, forecast at 9, forecast at 12, and the forecast at 15. So we can see how, well, even though this is a very variable day, the confidence intervals try to cope with the high variability of the signal. Now, the system can be adapted with this quantile regression approach. We can have less conservative confidence intervals. For example, instead of using just the 5% to 95%, we could use the interquartile distance, the 25% to 75%. Or we can have more points in the distribution, and that can be easily adapted in the model. That all depends on the application. Like, so there are applications where for trading, for example, you want to be less conservative and you want to have more risk, then you can tune the quantiles that you output. Or if you want to be more conservative, then you can just use this one and be sure that, okay, it's going to be with 90% probability that the forecast is going to be there. Just as a quantitative evaluation of the forecast, first we evaluated the reliability of the system. We use as metric the prediction interval coverage probability. We just measure, okay, how well are our confidence intervals. So this is the PICP for the forecasting horizon, and we see that is well, more than 90% for the whole horizon. And more as a global measure, we use the continuous rank probability score, which is measure, okay, how well the empirical distribution of the data matches the distribution of the quantiles. We use the normalized version of the CRPS, and we see that for the entire horizon, we have CRPS is smaller than 6%. As expected, the best CRPS is for short-term horizon, and it degrades over time. Now, we also benchmark this solution with a commercial solution based on satellite images and cloud motion vector tracking. This benchmark was made on 18 locations in Switzerland, all distributed for different zones and different climates, and also made on over 21 days, representative weather days for 1 year for the 4 seasons. On the right, we have a plot of the normalized root mean square error of the forecasting error against the forecasting horizon up to 6 hours. So in green, we have the error evolution of the smart persistent models. This is like the de facto benchmark model in PV or solar production. And in red is the error evolution of this commercially available solution for solar forecasting. And in blue are the results of Digerati. Now we can see that, let's say, for the first hour, the results of Digerati and the commercial solution are almost the same. But after that, you can see that Digerati has a decrease. And especially for 6 hours ahead, we can see up to a decrease of 25% in the error for this horizon. So it means that really like using ground sensors can really help into have a more accurate forecast. Now, one remark I wanted to make is that using GNNs can also accelerate the inference time and the computation time. Just in this particular comparison, the acceleration times were around 2 orders of magnitude, because in order to run the forecast for the numerical models, running these models are really costly. And then running the GNN, you can have inference with hundreds of nodes in just seconds, really. And also the training time is not that long. It's just a couple of hours, maybe 4 hours long to train the GNN with all the data. So it's not that long really. Now, we have a live demonstrator that is running live. This demo produces forecasts every 15 minutes for 6 hours ahead horizon. Of course, in the demo, we have only a limited set of nodes in Switzerland. If you want to try it, you can go or scan the QR code or go to this address, and you can play in the system. You can go to any node and see, okay, this is the past measurements or irradiance measurements at this node, and these are the forecasts, and you can compare what was forecasted, let's say, or you can see the future forecast. Or if you can contact me if you want access. One thing is that we have also an API available to get forecasts in real time for this. So if anybody's interested in trying it, just drop me a line also. One last thing I wanted to mention are preliminary results on extending this approach for day-ahead forecasts or for longer horizons. Now, one of the limitations that we have with ground-based measurements is the spatial context. We are basically limited by the boundaries of where we have our network of sensors. Now, one idea is, what if we use also like satellite images and combine the satellite images for a wider spatial context and use the ground-based measurements for having this local information of the signals. So we develop a physics-informed graph neural network that takes into account the advection diffusion equations of the process. And this physics-informed graph neural network takes past cloud concentration measurements. Based on this, it produces a forecast of the future cloud concentration. And how we use it in this preliminary approach is, okay, we pass to the encoder both like the data from power or irradiance from the network of sensors. And we also pass the past cloud concentrations sample at the nodes. And to the decoder, we pass the output of the encoder, but also we pass the cloud concentration sample at the locations. This is the results of this preliminary comparison. This is the NRMSE. Like in magenta is the error of the TSM GAT model that was shown before, and in blue it's the combination of ping and graph convolutional LSTM. That's another model that we have for forecasting. And we see that there is a reduction of error, but more than that is that it's promising for longer horizon. Now, just to conclude my talk, well, I introduced the Digerati solution that we developed at CSEM. This solution is based on a ground-based sensor network that uses data from PV systems and from weather stations. It uses graph neural networks to learn the spatio-temporal relationships. And also, most importantly, is robust to changes in the data itself and in the node set, and it can fill gaps in the data. As I said, one of the outlook is to include other heterogeneous data sources, such as numerical weather predictions or satellite images, to extend both the spatial context and to increase the prediction horizon. Well, thank you very much for your attention.